Oh yes, this monstrosity. Sadly, I made a sliver. Garrett. It was here.
Oh, sorry.
It's here, right? So we shifted down by 2. Right, so that n does become n plus 1, but that n minus 1 shouldn't be n. It should be n plus 1. Nothing else changes, thankfully. Other than I just have to fix my recurrence relation. And they wanted the first 3 non-zero terms, right? So A naught, A1, everything's going to be in terms of A naught, A1, and it looks like A2. But A2 is 0. Oh good, we have the first 2 non-zero terms. Actually, I think we're even better than that. We have that negative A naught x minus A1 x squared. A2 is 0, so that goes away. A3 is A naught over 6, right? So that is just A naught x. Oh, bummer. Oh, I'm sorry. That's not what I'm doing. I want to come up to here. That is why. So we have A naught and we have A1. We have 2 terms. We just need 1 more. Lots of my eraser not working now. I'll write it up here, I guess. N equals 0, you get A naught x to the 0, which is just A naught, right? N equals 1, you get A1 x to the first power. N equals 2, it's A2 x squared, but A2 is 0. So that doesn't count. we need A3, which is A naught over 6. X cubed, there's the first 3 non-zero terms of your solution. So thankfully, we didn't even need that recurrence relation. We didn't have to go up that far. And I'll just do that to signify, right, the solution would actually continue on forever because it's a power series. They just wanted us to write the first 3 terms. You could combine this. Right, and if you wanted to, you could use C sub n instead of A sub n. If you're more comfortable using C's like we've been doing, but it doesn't matter. There you go, that's the solution. If you needed more, we had to go past A4, that's where you have to use the recurrence relation we found. And that would give you each term. And now here's where it becomes a real pain. If they actually want the entire power series, you have to solve that. Which means you have to find a general solution for A sub n based on that recurrence relation. And that is a nightmare to do. I will make a comment. I did write the exam. I'm pretty sure there's nothing that says you have to find the entire power series. It's always like find the first 3 non-zero terms or find up to the x to the whatever. And also when I wrote it, I forgot homogeneous linear systems. That was supposed to be covered, so I'm not going to cover them on exam. That'll be on. Which because that's also kind of people miss this up. General solution up to x to the 6th. Right, so they only want up to the x to the 6th term. Right, that is always your first step. Start with the infinite series a sub n x to the n. Then you just take however many derivatives you need. Right, third derivative, if you need it, would just be n equals 3 to infinity, right? N minus 1, n minus 2, a n x to the n minus 3, so on and so forth. Then just plug them back into the original equation. Y double prime. Plus x squared times y. Remember, that whole thing's going to have to equal 0. Is that the same as what we had here? That was minus x times y. Now the idea is you want to write that as a single power series. With, why did I do x sub n? Obviously, your indices have to start the same, and you also want the same power for x. Generally, try and write it as x to the nth power. And save yourself a headache. Don't distribute your n's, right? Even if you go to the third derivative, just leave it as n times n minus 1 times n minus 2. If you remember what we did here, I never distributed it. I even left it in the recurrence relation as n plus 1 times n plus 2. Zero. To make that first term x to the n, just shift the index down by 2 units. Which means wherever there's an n, you're replacing with n plus 2, right? Become n plus 1 times n plus 2. That x to the n plus 2 is going to be a problem. I need to, okay, so that may not be what I wanted to do. So I'm going to need to shift that up 2 units, right? Which would then start me at n equals 2. So I think what I'm going to want to do is take out the first 2 terms of that first series. You'd then be left with starting at n equals 4, and then shift that down by 2. And then everything would match. So let's just do this, and so that was a mistake. So instead, take out the first 2 terms. N equals 2. 2 times 1, right? 2. A sub 2, x to the 0. That's for n equals 2. N equals 3, it's going to be what? 3 times 2 is 6. A sub 3x. that has to equal 0. Now shift that to be x to the n, which means I'm shifting down by 2. I want that to be x to the n, so I have to shift up by 2. Now we can write that as a single power series. Both A2 and A3 have to be 0. That doesn't seem right. Oh, never mind. Right, so you're going to get 3 equations out of this, right? And then finally that. And then the currents relation. Now up to the x to the 6th term. There is no A2 and no A3. I'll write them out for now. Because that's what we want. Of course, that's 0. That's 0, so they just disappear. We're going to have to use the recurrence relation to find A4, A5, and A6. A4 is when n equals 2. So let's do that. A sub 2 minus 2, right? A naught over 2 plus 1 is 3. And 2 plus 2 is 4. There's A4. Just delete that and say we did an array. A5. Well, that would be when n is 3, right? A6. N equals 4. Stop. A sub 2, 0. Which doesn't match this. I'm just going to assume that they're wrong, because I don't think I need any arithmetic or algebra mistakes here. I got the same recurrence relation.
How do you get what's in the parentheses? For the final answer?
These, I just factored out the A0 and the A1s. So my A0 terms right here, A0 and
I see.
A4. So I just factored it out.
Got it.
Is that necessary? No, but it does keep it in the form, right? So you know you should have 2 linearly independent solutions. And your general solution is the linear combination of them, right? Well, look, there's your first one, attached to the A0, and there's your second one, attached to the A1.
Well, you solve for A0.
They weren't given, were they? When we did all the work, there was nothing in here saying what A0 and A1 should equal. It started with A2. So A0 and A1 are just arbitrary constants. They can be anything. No, what's that? The hell's that shape there? No idea what happened there. They only went up to x to the 4th, and now we have initial conditions. Use the initial condition right away. That's what your sum would be, right? Factor out the 0 term, so a naught plus that sum. But each of those has an x now associated with it, doesn't it? That entire sum goes to 0. A naught's going to have to be 1. And 1 times a sub 1 times x to the 0. And again, each of those terms in that sum now has an x associated with it. At 0, that sum just goes to 0. Which means a1 will have to be 0. Now we know what a naught and a1 are. Now it's the same process. Except we actually have values now for a naught and a1. Y double prime plus x times y prime plus just y. That will have to be 0. Distribute that x through. I think what we're going to have to do here is try and write everything in terms of x to the n minus 2.
So you too.
Thank you. Yeah, and then we're going to start it at equals 3. That's what it looks like we're going to have to do. But for now, I need to make that n x to the n minus 2, which means I have to shift up by 2 units. Just have to take out the first term of the first sum and of the second sum. That would leave us with what? A sub 2, 2 times a sub 2, right? Plus that's not good. Oh, never mind. They're both constants, okay. Good. Because that's just going to be a naught, right? Now all the sums start at n equals 3, so write them as a single sum. Oh. But these are both in terms of a sub n minus 2, right? Simplify. N minus 2 plus 1 is just n minus 1, right?
How is what's in the brackets all to n equals 3? Where did you put that?
Well, I factored out the first term of the sum.
Mhm.
So what happens when we take a term of sum out? The effect goes up by 1, right? Because what we essentially did here was I just took out the n equals 2 term. That's this here. So it's this plus this sum, but now n equals 3 to infinity instead. Same thing here.
So then I guess by plugging in, because you ended up taking out the terms.
Yep. Which shifts it up. Now they all start at n equals 3, so you can write it as a single summation. Two a2 plus a naught has to be 0. And then finally, the recurrence relation. Is that a sub n? Yes. It's a n minus 2. That has to equal 0. A2 is negative a naught over 2. And our recurrence relation oh, that's a nice one. Right, because your n minus 1s are going to wind up dropping out. Greater than or equal to 3. But what was a naught? 1, right? A naught plus, right, because again, I'll write it out. What we're doing is we're doing this, right? to the x to the fourth? A naught's 1. A1 is 0. Gone. A2. Negative A naught over 2, but A naught's 1. Now we need A3. Be negative A1 over 3, right? Oh. A1, 0. So that's 1. A4. Negative A2 over 4. Oh, what was A2? It was negative A naught over 2. Right, so let's just come and write that out. Which makes A4, what, A naught over 8? But A naught is 1. This thing won't be the entire general solution. Thankfully, it's an initial type problem. Using the same argument, you're going to wind up with the initial conditions giving you A naught being 2 and A1 being 0. Plug everything in. Distribute through. again, it looks like we're gonna have to get everything into x to the n minus 2. We need to factor out, we need to take out the first term of first and third sums again. 2 raised to the 2 plus 2. Okay. Sorry, that n minus 2 shouldn't be there, should it? We're going to have a 2n minus 4 plus 2, right? Two n minus 2? Or two times n minus 1?
When did it shift from minus to plus? Because the original equation is minus.
Where?
Like that bottom series or sums, and then the top. They're all added, but then before the second two were subtracted. So I don't know if that's something.
Oh, were they? Oops, yeah, you're right. It should have been minus. That makes this a minus, right? It's going to change to this. That should just be a minus instead, though, right? Bummer. Out of time. I don't need that x to the n minus 2 there. Alright, those are your two equations that you get. Gives you the recurrence relation and A2 in terms of A and all, so you should easily be able to solve it from there. into your groups. So that's a little behind, but whatever. Like I said, I am not covering singular points. I'm not covering solutions around a singular point. For instance, x equals 0 being a singular point. Right, so something like y double prime plus 1 over x times y. X equals 0 is not singular. That is a completely different method called the method of Frobenius, and the algebra is like 3 times worse than what we did. So now we're going to move on to systems of first order equations. This is going to require us to do linear algebra. Right? Specifically, now we're going to be looking at determinants and eigenvalues, eigenvectors. But to find eigenvalues, you need to do what's known as row reduced echelon form, RREF. For today, we're going to do it by hand. Once we actually get into applying it, this is why God invented mathematics. So we're going to be using a calculator to actually do all that for us. It'll save us a lot of time, I should say. But for today, we're going to do it all by hand, just so we appreciate the calculator more. Unless you've already had linear algebra, then you already know how much of a pain it is, and you already appreciate the calculator. In which case, I apologize if we bring back some trauma. But the good news is, I think I only go up to 4x4. For the most part, I think most of the first order systems are 3x3 max, if I remember correctly. So this is the definition of row reduced echelon form or reduced row echelon form. They're used interchangeably. The idea of an elementary row operation. There are 3 of them. Interchanging 2 rows, multiplying a single row by a non-zero constant, and then replacing a row by the sum of that row and a multiple of another. All right, and every matrix has a row reduced echelon form. I'll cut off too much there. Furthermore, that's row echelon form. There's also row echelon form. Right, so every matrix is row equivalent to a matrix in row echelon form, which is not necessarily going to be unique. However, every matrix is going to be row equivalent to a unique matrix in reduced row echelon form. That's key. Here's the definition of an eigenvalue. You have a square matrix. You have a non-zero solution vector K, right, or some non-zero vector K. Then any number lambda such that AK equals lambda K is an eigenvalue of the matrix A. K is an eigenvector corresponding to that eigenvalue. I will probably not be using K. I actually do need to change that order. You can rewrite AK equals lambda K as either lambda I minus A times K equals 0, I is your identity matrix, or A minus lambda I times K equals 0. For linear algebra, that order doesn't matter. When we actually go to apply it, the order does matter. The technique we're going to be using we need it to be A minus lambda I. And obviously then this determinant would be A minus lambda I equals 0. That is called your characteristic equation. All right, so the characteristic equation is used to find all the eigenvalues for your matrix. To find eigenvectors associated with that eigenvalue, you plug it back in to A minus lambda I, RREF that, and solve the resultant system. That will then give you the eigenvectors. And in theory, there's an infinite number of them. Now we get into systems of first order differential equations. We focus on just first order in this course. Higher order is a bit worse to solve, even if it is linear. That is said to be your normal form. Right, it's where you have each of the independent variable derivatives equaling something in terms of the n independent, or the n dependent variables, right? The x, the x1, x2, x3, x4, so on and so forth, all of a single independent variable t. In the case where each of those f sub i's is 0, it's called an homogeneous system. Then obviously, if they're not all 0, it's called non-homogeneous. The general method of solution is going to be the same as we did for just the linear systems. Except we're now using eigenvalues. So you get a complementary function, which is found by solving the homogeneous component, and then you have to use a method to find your particular solution. There's only one method that we study, and that's called variation of parameter, but for systems. And it is a bloody nightmare without a calculator, because it involves inverse matrices and products of matrices and then integrating a matrix. It's awful. Just finding the inverse of a matrix by hand is terrible. Generally speaking, we like to represent systems in matrix form. So we'd say capital X is your solution vector. That is your vector x1, x2, down to xn. And note in linear algebra, we write vectors as column matrices, not like you do in Calc 3 or physics. Then you have what's known as your coefficient matrix A, and your capital F of t would just be the F1, F2, that vector. Then we can write our normal form as just the vector x dot equals ax plus f. Yes, there's a very small dot above that x on the left-hand side. Solution vector, use capital Phi, I'll probably just stick with x's. Doesn't matter. Is obviously just any vector that satisfies that equation, that system. And again, think back to solving just regular old systems of linear equations in algebra. Your solution x, y, z, however many there were the values that satisfied all three equations simultaneously. Same idea, except now we're dealing with differential equations. And of course, you can have initial value problems as well. Right, except now, your initial values are going to be vector form. Right, and because it's first order, it's just going to be the vector x of 0. That's the only initial value to be given. So x1 of 0 equals something, x2 of 0 equals something, x3 of 0 equals something, so on and so forth. Right, existence, and stuff the superposition. Right, so again, it's the same idea that you want to find if you have n equations in n unknowns. You'll have n linearly independent solutions, and any linear combination of those n linearly independent solutions is also a solution. So the general solution would just be C1 times your first, plus C2 times your second, so on and so forth. Now, okay, same thing, that's what it means to be linearly independent. Set of vectors not linearly independent, or that's what it means to be linearly dependent. Any set of vectors that's not linearly dependent is said to be linearly independent. Linear algebra would define it for independent, and then say if it's not, it's dependent. This uses actually vector spaces, what it means to be linearly independent in a vector space. So you cringe a little bit. Yeah, sorry. We're using a different test in this course than you would in linear algebra. We once again call it the Wronskian. And there's your Wronskian. It's the determinant. I don't think those should be pluses. I think those should be commas. Right, but you have n vectors. The Wronskian is found as the determinant of the matrix where each column of the matrix is that vector. Right? So the first column is phi1, second column is phi2, so on and so forth. That determinant. If that determinant is non-zero, then they're linearly independent. Right, and just as before, all you have to do is show that the Wronskian is non-zero at a single point. It will then be guaranteed to be non-zero everywhere. If it is 0, then they're dependent. Right, they're linearly independent. It's called a fundamental set of solutions, just as before. And the solution of a homogeneous system is just the linear combination of your linearly independent solutions. Then for the non-homogeneous systems, you have your complementary function, or complementary vector, let's call it, which you find from the homogeneous part. Then you have to find a particular solution, and your general solution is the sum of those two. We won't worry about finding the solutions until next time. The rest of this will just be practicing finding eigenvalues and eigenvectors. Which again, we shouldn't have to do because it should be a prereq for this course. But here we are. After review linear algebra, I could do some numerical solutions, teach you some numerical techniques in coding. Find all eigenvalues of the matrix and find an eigenvector associated with each of the eigenvalues. Notice it says find an eigenvector, just a single one. When we go to do solutions, that's all we need. We just need a single eigenvector. Whereas in linear algebra, you have to find the basis for the eigenspace, which means you need all the eigenvectors. You need your eigenspace itself. I like eigenspaces, they're fun. First thing I want to do is find that determinant. Do this determinant of, and I'm not going to write this out every single time. I'm just going to do it for this problem. There's your 2 by 2 identity matrix. 1, 0, 0, 1. Now remember, we already looked at basic matrix operations. Right? We did that back with linear systems. No, you don't have to use lambda for your eigenvalue. You can use anything. X is commonly used. I stay with lambda because that's just what I learned. Say that's what I grew up with. And remember, absolute value bars around a matrix means determinant. And from now on, I'm just going to skip right to that because the process is almost identical. Right? The only thing that's changing is your area and possibly the size of your identity matrix. For a 2 by 2 matrix, it's easy, right? Main diagonal, that product, minus the off diagonal, that product. Remember, this whole thing has to equal 0. Lambda squared looks like minus 7 lambda. And then plus 10 total. Right, it'd be plus 12 minus 2. And that whole thing has to equal 0. This here is called your characteristic polynomial. Right, then equals 0 is the characteristic equation. What I'll do is copy this to the next line. Solve it. Now, I want you to notice something. What was the size of that matrix? What's the order of our polynomial? Which means it's going to have how many roots? So if you account for multiplicity. Huh. I wonder if that's always the case. You don't get the answer. You have to bring around to 0 now. In fact, it is. Take linear algebra to see it. I think it's proven in linear algebra. You haven't even gotten there yet.
I think we're getting.
Eigenvalues is typically the last thing you do. Well, one of the last things you do. Depends on how it's taught.
We're close to that.
So you're still a ways off.
Yeah, I guess so.
So it's typically only a week and it's like a week, maybe a week and a half in the standard 15 linear algebra course. But you're gonna have an advantage because you're doing it now. So you can show off. It's obvious. Everyone knows this. Teaches them pre-calc. Can that be factored using integer coefficients? What is a factor to?
-5, -2.
We have two distinct eigenvalues. Now we need an eigenvector for each one. For the eigenvalue 2, go back to that matrix, A minus lambda I. So it's going to be what? 2, 1, 2, 1? Oh, that's beautiful. You want to row reduce that. You should easily see what that row reduces to, because you've got linear algebra. For those who haven't, I'll go over the process of row reduction. You look in your matrix. Look at row 1, column 1. Is that non-zero? Yes. There's your pivot. Is it 1? Make it 1. You don't have to. But when you're first learning it, it's a good idea to do it. Just stick with the process. That's done by multiplying row 1 by a half. Now you want to zero out everything below that pivot. Well, to make that 2 0, it would just be -2 times row 1 plus row 2, right? You now have a row of zeros and there's nothing under it. You're done. That's your RREF. This gives us a system of equations, specifically this system. That second equation, though, is what's known as a tautology. It's always true. It doesn't add any value, so you can just ignore it.
But couldn't we just subtract row 1 minus row 2 from the start?
You can.
Would it get us the same answer?
You'd still have to multiply that first row by half, because it has to be a 1. It has to be a leading 1.
Oh, it has to be a leading.
But you could do negative row 1 plus row 2 first.
There's different ways to go. That's not.
I'm just going over what the process actually is in linear algebra. When you first learn it, it's always you make it 1 first and then 0 out. But as long as you get it to be the proper form, it doesn't matter how you do it. That'll give us x1 is negative x2 over 2, right? And x2 is free. It's a free variable. Now again, I'm only going to do it for this problem. The eigenspace is the set of all of your eigenvectors plus the 0 vector. I'm just going to look at the set of eigenvectors. I'm going to call that lambda 1. It's all vectors of the form negative x2 over 2, x2, where x2 is any non-zero real number. Remember, eigenvectors have to be non-zero. Those are all of your eigenvectors associated with this eigenvalue. You just want one of them. So pick any non-zero number. 2. There's an eigenvector. But that was for the eigenvalue 2. We have another eigenvalue. Same process. A minus lambda I, 4 minus 5 is negative 1. So you get negative 1, 1, 2, negative 2. Now RREF that. Again, if you have linear algebra, you already know what that RREF is going to be. It's really obvious. Going through the process, that's your pivot. Make it 1. How do you do that? Multiply by negative 1, right? Now you want to zero out what's below your pivot. Negative 2 row 1 plus row 2, right? That's now row reduced. That corresponds to this system. x1 minus x2 equals 0, 0 equals 0. Again, that 0 equals 0 is a tautology. Doesn't really add any value to our system. The solution to that system is x1 equals x2, and x2 is any real number. Set of all of our eigenvectors set of all vectors of the form x2, x2, where x2 is any non-zero real number. We want a single eigenvector. Again, you can choose any non-zero value for x1. Why not choose 1? There's an eigenvector. And you're done. That is what's known as the eigenproblem. And that is what we'll be doing to solve systems of first order equations. So in other words, you should be having nightmares about this lesson or not. You do it a lot. You even more so. Because you're doing this a lot in linear algebra too. Actually, I think I'll do. So the homework journal 10 assignment I put up, that covers homogeneous systems. And since that's not going to be on this exam, I think I'll just push that homework to be due with the third exam. And so the homework that's for this week, the 10.1, 2, and 3 will be the last thing for the exam for the homework journal that I'll be collecting. So I'll adjust my grading sheet as well. Same thing, different matrix. And now I'll do the short version. That's the term we want to take, right? Negative lambda, negative 2, 3, 1 minus lambda. Lambda squared minus lambda plus 6 equals 0. That's the characteristic equation. Can that be factored with integer coefficients? The answer is no. That's a bummer. Oh, bummer. We get complex eigenvalues. This should be new, even if you've had linear algebra. Elementary linear algebra does not consider complex eigenvalues. More advanced linear algebra, of course, will. Because in linear, elementary linear, you're looking at matrices only in the real number field. But who said your matrices had to only have real numbers? They actually can be anything from any field. Complex numbers are a field. That's what we're working with in differential equations. But the process itself is still the same. Start with that. Negative lambda that was what? -2, 3, and then 1 minus lambda, right? 1 minus a half. This is not so simple. Or not as simple to row reduce than if everything is real. Boy. So the first thing I'm going to need to do is take that pivot and get rid of the complex component. How do you get rid of it? Well, that's very easy. What do you mean by flip?
Take the column 2, replace the column. Like,
Oh, I could do that. I'm not going to. Because you're still ultimately going to have to do something to get rid of it. No, it's very easy. Just multiply by the conjugate. That will turn that first entry into a real number only. It gets rid of your imaginary value. Because the difference is squared. So what's negative a half squared? Quarter. Then it's minus root 23 over 2I squared. Which is what? 23 over 4I squared. Or what's I squared? It's -1. A quarter minus 23 over 4. Negative 22 over 4. Which is negative 11 halves. Oh, this is gonna get really hideous. I can already see it. I may just go to the calculator. That's why I hate it. Let's see. Then we'll get what? 1 minus root 23i. The next step in the process is now to make that negative 11 halves 1. So you can multiply by negative 2 11ths. 1. That's going to be a problem. So I multiply by negative 3 and add. That's not going to zero out. Uh-oh. Uh-oh.
What are you doing? What are you doing? I don't know. No, I have to drop off something. I have to pick up that email. I have to go and then go to the this is fun. It'll be like exciting. I gotta catch a flight. I'm happy. Just they're back to their days.
the identity matrix.
That's what it should be. Way too long stuff, complex matrices. Authorize on the flow sheet. So that is what they did. They swapped row 1 and 2 and then went from there. Oh, good. Something right there. So I'll leave that arithmetic up to you. So go back to the original. They flipped row 1 and row 2, and then proceeded. Still not going to be fun, but there's what we got. That's a lambda 1. which will give us actually, we actually use 6 to get rid of the fractions. Make my life better. That'll be the eigenvector. Which for our purposes, we're not going to want to keep it in I. We'll convert this, when we find the second eigenvector, we'll convert it to real value vectors later. And that'll be done when I actually look at the solutions. For now, that's fine. Your job is to find the eigenvector associated with that second eigenvalue. So you'll find x2 on your own. I would recommend just using a calculator to reduce when you plug in the complex eigenvalue. This is where we'll pick up on Thursday. We'll look at 2 3x3s and then a 4x4. Let me just put this up here. There's only one more group assignment. It's going to cover this stuff, systems of linear equations, as well as Laplace transforms. So that's not going to be due until the 12th of August. And that's the class before our final. Fourth quiz will go up after next Tuesday's class. And I'm pretty sure I forgot to put in homogeneous systems on that quiz as well. So that may not cover homogeneous systems. Second exam is next Thursday. First time in minutes of class, so make sure you show up on time. And again, it will not cover what we start doing on Thursday. It won't cover the homogeneous system solutions. Just the theory, like what we're doing today and what we'll finish up with on Thursday. See you on Thursday.
Yeah, we get a question on